Hello everyone, and welcome. Today, we're going to revisit some key ideas from our previous physics lessons. This is our first slide, the cover slide, titled Last Time Revision. We'll be focusing on the 10 important big questions in physics that we've explored before. So, in this presentation, I'll briefly go over those questions and what they mean for our understanding of the physical world. Let's get started and refresh those concepts together. Let's talk about the different types of inertia and understand what they mean in real life. First, we have the inertia of rest. This means that a body at rest tends to stay at rest. For example, when a bus suddenly starts moving, you might feel yourself lurching backward because your body wants to remain stationary. Next, there's the inertia of motion. This is when a moving body keeps moving at the same speed and in the same direction unless acted upon by an external force. For instance, if the bus suddenly stops, you might fall forward because your body is trying to keep moving forward. Finally, we have inertia of direction. This means that a body resists changing its direction of motion. Think about when a car makes a sharp turn. Passengers tend to lean sideways because their bodies are resisting the change in direction. These examples help us see how inertia is all about resisting changes, whether in rest, motion, or direction, which is crucial to understanding how objects behave in our everyday world. Let's delve into the law of conservation of linear momentum. The core idea here is that the total momentum of a system remains constant, but only when no external forces are acting on it. This means that within an isolated system, momentum can change from one part to another, but the overall total stays the same. To understand this better, consider a simple example with two bodies. Let's say the first body has a mass m1 and an initial velocity u1, while the second has a mass m2 and an initial velocity. After some interaction or collision, their velocities change to v1 and v2 respectively. Now, according to Newton's third law, remember, for every action, there's an equal and opposite reaction. This interaction ensures the total momentum before and after the event remains unchanged. Mathematically, we express this as the initial momentum, which is m1u1 plus, equals the final momentum, m1v1 plus m2v2. And that's the key point. Initial momentum equals final momentum. This equality is what we call the conservation law, and it's fundamental in understanding how objects interact in physics. So, in essence, we've just proved that momentum is conserved in an isolated system, which ties beautifully into the overall theme of how energy and momentum behave in the physical world. Now let's take a closer look at the construction and working of a compound microscope. At its core, it has two main convex lenses, the objective lens, which is placed near the object we're examining, and the eyepiece lens, which is near our eye. These lenses work together to magnify tiny details that we can't see with the naked eye. Other important parts include the body tube, which holds the lenses in proper alignment, the stage where the slide rests, and a mirror that helps direct light onto the object for better visibility. When we use the microscope, the object is placed close to the objective lens. This lens then forms a real, inverted image of the object, meaning the image is upside down and reversed. This is a key point because it shows how the lenses manipulate light to produce a clear image. Next, the eyepiece lens magnifies this real image, making it appear much larger to our eyes. The final image that we see through the eyepiece is virtual, meaning it's not projected onto a screen, but appears to be inside the microscope. This virtual image is inverted again, so it's upside down relative to the original object, but it's also highly magnified, allowing us to observe tiny details in great detail. Overall, the combination of lenses and their arrangement allows us to see things at a microscopic level that would otherwise be impossible to observe with the naked eye. In this slide, we're looking at an experiment designed to measure both the real and apparent expansion of a liquid as it heats up. The main goal here is to understand how the liquid's volume appears to change, as well as how the container itself expands with temperature. To set up the experiment, we use a glass flask filled with the liquid and a capillary tube attached to it. The capillary tube is crucial because it allows us to observe small changes in the liquid level very precisely. We also have a thermometer to monitor the temperature during the process. The procedure involves filling the flask with the liquid, fixing the capillary tube in place, and then marking the initial level of the liquid in the capillary. Once everything is set, we heat the flask gently. As the temperature rises, the liquid expands and pushes up in the narrow tube, so we note the new level. The key point here is understanding the difference between apparent and real expansion. The apparent expansion is what we observe in the liquid level increase, which is the liquid's expansion minus any expansion of the vessel itself. The real expansion, however, accounts for both the liquid's expansion and the vessel's expansion, so it's the apparent expansion plus the vessel's expansion. Imagine the diagram: a flask with a narrow tube attached, initial level marked, and then a final level after heating. This visual helps us understand how the liquid rises as it expands. This experiment is vital because it helps us distinguish between how much of the volume change is due to the liquid itself and how much is due to the container expanding. This distinction is important in many practical applications, such as in thermometry and material science, where precise measurements are essential. A nuclear reactor is essentially a device used for controlled nuclear fission, which produces a significant amount of energy. Now, let's go over its key parts and their functions. First, we have the fuel, which contains the fissile material that undergoes fission. Next is the moderator, whose role is to slow down neutrons, making them more likely to cause further fission reactions. Control rods are inserted or withdrawn to control the reaction rate. They absorb excess neutrons and help keep the process safe and steady. The coolant circulates through the reactor to remove the heat generated during fission, preventing overheating. Shielding is also crucial. It provides safety by protecting operators and the environment from radiation. So how does it work? Fission generates heat, which is then used to produce steam. That steam drives turbines, and the turbines generate electricity. Remember the acronym FMCCS: fuel, moderator, control rods, coolant, shielding, as a helpful way to recall these essential components. In summary, a nuclear reactor uses these parts working together to produce energy efficiently and safely. Let's start with the series connection. In this setup, the circuit diagram shows a battery connected to 3 resistors, R1, R2, and R3 in a line, one after the other. The key point here is that the current, which we denote as I, remains the same through all the resistors. However, the voltage gets divided among them. Using Ohm's law, we see that the voltage across each resistor is V1 equals IR1, V2 equals IR2, and V3 equals IR3. When we add up these voltages, the total voltage across the entire circuit becomes V equals V1 plus V2 plus V3 substituting. That's V equals IR1 plus IR2 plus IR3, which simplifies to V equals I times the sum of the resistances, R1 plus R2 plus R3. Since V equals IR, we can then write that the equivalent resistance R in series is simply the sum R1 plus R2 plus R3, so the final formula for resistances in series is R equals R1 plus R2 plus R3. Now moving on to the parallel connection. Here, the circuit diagram shows the battery connected to 3 resistors, R1, R2, and R3, each in its own branch, all connected across the same 2 points. The key point here is that the voltage across each resistor is the same, which is V, but, unlike the series case, the current gets divided among these branches. Applying Ohm's law again, the current through each resistor is I1 equals V divided by R1, I2 equals V divided by R2, and I3 equals V divided by R3. When we add these currents, the total current I flowing from the battery is I equals I1 plus I2 plus I3 substituting. That becomes I equals V divided by R1 plus V divided by R2 plus V divided by R3. Factoring V out, we get I equals V times the sum of the reciprocals of R1, R2, and R3. Since V equals IR, we can write that the reciprocal of the equivalent resistance R is the sum of the reciprocals of R1, R2, and R3 so. The final formula for resistances in parallel is 1 divided by R equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. Understanding these two configurations helps us analyze circuits more effectively, depending on how the resistors are connected. Thank you so much for watching, everyone. Before we wrap up, I want to leave you with a big question to think about for our next discussion. This question really ties together everything we've explored today about chemistry and its role in our world. So, I encourage you to ponder it deeply and come prepared to share your thoughts. Remember, understanding these big questions helps us see the bigger picture and appreciate the importance of chemistry in everyday life. Thanks again for your attention, and I look forward to continuing this fascinating journey with you next time.